Good morning, everybody. Welcome back. I hope you've had a good week so far, and that things have gone well for you. There's a few announcements before we get into our lesson for today. I guess the most important one is we have a date for the AP exam now. We're going to be doing Administration 3 for the AP exam, and it will happen on June 10th for AP Stats. We'll get more details about time and how we will take that. This will be a digital exam. It will, I believe, from my understanding, there will be a little bit more multiple choice than the normal pencil and paper exam. And the free response questions will be such that you will be able to type your responses. You will not be able to take this exam on a phone. You must use like a laptop or desktop computer. You will have the option to take it at home or come to a campus and take it on campus, but it will be digital no matter how you take it, as far as like at home or on campus. So if you're taking the AP exam, that is the date for the AP Stats exam. It is June 10th. All right. We will be able to like play around with the digital testing interface and all that stuff starting in April. So we'll be able to do some stuff like that while we're in class to see what that's like, how it operates and things like that. So that will be forthcoming next month. So please keep that in mind. You might want to put that on your calendar. So again, the date is June 10th, and it is in our calendar on the course on the front page. All right, so here we go. Other thing, what else? So, testing. Okay, other thing that's going to be wacky over the next couple weeks is the district has decided to return to campus. And so next week, so that teachers have an opportunity to actually have classrooms that are prepared to receive students, because none of us have been in our classroom for over a year. We're going to have days that we are getting our classrooms ready and doing mandatory trainings and things like that. So what that means is next week for you guys will be entirely asynchronous as far as my class is concerned. There will be a Monday T lesson. Tuesday will be a normal 1 through 5 day, and then Wednesday, Thursday, Friday will be entirely asynchronous. There will be no live class meetings scheduled, as far as I understand. If you're not sure about that, please check with your teachers, your other teachers for other classes that meet that day. That's my best understanding. We're supposed to learn more today. So I can update you tomorrow if anything is different than what I said today. So please keep that in mind, that it will be like over a week until I see you again after tomorrow. As far as any live session, I'm planning to have just resources for Chapter 9 available for you guys. But mostly you should be using that time to get caught up in this course. Other courses, I'm not going to assign anything new past what we covered today in class. There'll be resources. All of Chapter 9 will become available next week, but I will not expect you to submit anything besides things that have already been assigned. So there's that as well. Any questions, concerns, anything like that?
So right now, well, us that have online classes, you're gonna be going back to school, and us as well?
I'm not 100% sure. I believe that if you selected to be online, that's going to remain that way, because that was your choice at the semester, was to stay in an online-only environment. So I believe you'll remain online. Because that was the option you chose. Students who had selected the hybrid model in the event that we return to campus are the ones that I believe will return to campus.
Okay, thank you.
You're welcome. But I'll get clarification on that and I'll let you know tomorrow. You write a note so you don't forget. Okay. All right. Any other questions, comments, concerns, clarification you would like, either about the AP exam or returning to campus kind of stuff? Alrighty. Okay, so then we are going to start chapter 9 today. We completed chapter 8 last week with our lesson on section 8.3. The chapter 8 assessments are available. Some of you have done them, some of you have not. That is what it is. Please remember, you will never get penalized for turning in an assignment late, but there is a point at which I put in a placeholder grade based on it being not submitted that will give you a reflection of what your grade will be if it's not done. Always, once it's done, it'll get graded, your grade will be updated, no penalty. So just keep that in mind as well over the next couple weeks. So yeah, we're going to start chapter 9, starting with section 9.1. So if you do have something you're taking notes in, please have that ready. We're going to start the chapter about testing a claim. Alrighty. So here we are, chapter 9, testing a claim. 9.1 is our introduction to significance tests. It is not specific to proportions or means or any other parameter / statistic. It is just about the concept in general. Section 9.2 and 9.3 will deal with specific rules and things dealing with proportions and means, just like the previous few chapters have. So our goals today is to be able to state the null and alternative hypothesis for a significance test about a population parameter. We want to be able to interpret a p-value in context, determine whether the results of a study are statistically significant, and make an appropriate conclusion using a significance level. We need to be able to interpret a type 1 and type 2 error in context and give a consequence of each. Right? So things that might be new: the null and alternative hypothesis, significance test, p-value, significance level, type 1 and type 2 errors. Right? We'll get all the definitions for all those things today, and we'll see some examples of what they are. But first, what we've used so far is a confidence interval. Right? And that's one of the two most popular, most common types of statistical inference. We use confidence intervals when our goal is to estimate a population parameter. And that's what we did in the previous chapter. We wanted to estimate the population proportion or population mean. So we use a confidence interval. The second common type of inference, called significance tests, has a different goal. It's to assess the evidence provided by data about some claim concerning a population. A significance test is a formal procedure for comparing observed data with a claim, also called a hypothesis, whose truth we want to assess. The claim is a statement about a parameter, like the population proportion p or population mean mu. We express the results of a significance test in terms of a probability that measures how well the data and the claim agree. Okay, so this is the idea. We use significance tests to test a claim. Right? If someone says that they are successful at something 90% of the time, we want to test that. We want to take a sample, do some math, come up with a probability of that thing actually happening, and how does it compare to the claim. We'll make a conclusion. So that's the general idea. So we're going to look at this applet here. That's from our publishers. And it's based on a basketball player who claims to make 80% of the free throws that he attempts. We think he might be exaggerating. To test this claim, we'll ask him to shoot some free throws virtually using the reasoning of a statistical test applet on the At the Books website. So we're going to go into this applet. We're going to set it for 25 shots. We're going to tell it to shoot. We're going to record how many of the 25 shots the player makes, which the applet will do for us. We'll click shoot again for 25 more shots. We're going to repeat this until we are convinced either that the player makes less than 80% of the shots or that the player's claim is true. And then we'll check show true probability and see if we were correct. All right, so that's where we're going to go, which I totally forgot to have this open, so give me a second. Properly set up, that would have been good to do. Here we go. So here's our app. We're going to set this for 25 shots, and we're going to shoot. And it's going to say that he got off to a rough start. And after 25 shots, he's got 64% made, 36% missed. We've only got a sample of 25. It seems like he's kind of trending up. Maybe he just had a rough start. We'll do 25 more. And we're at 56% and 44%. Starting to look like he was probably exaggerating. We'll do one more set of 25 just for good measure. It's not looking good. All right, so it looks like he made 41, missed 34. He's at 55% to 45% misses. His claim was that he makes 80%. Our evidence basically says that he is exaggerating. Based on our sample, the true probability is right around 50%. All right, so this is kind of a short simulation showing like, okay, we had a claim. We tested the claim by taking a sample of 75 shots. Based on that sampling, he only made 55% of his shots. We don't really have good evidence that the claim was true, right? Based on the evidence, we would say that his free throw percentage is less than 80%. All right, so this is what we're going to be doing. We're going to be testing claims. Excuse me. So the very first thing we need to be able to do when we're going to test a claim is we need to state hypotheses. Right? A significance test starts with a careful statement of the claims we want to compare. Right? There's a claim, and then there's the other thing that we think might happen. The claim we weigh evidence against in a statistical test is called the null hypothesis. Often the null hypothesis is a statement of no difference. In the basketball example, the null hypothesis would be the 80% making of free throws. The claim about the population that we are trying to find evidence for is the alternative hypothesis, making less than 80% of the free throws. Right, and we use the notation H sub 0 for the null hypothesis, and that's because null is like 0, nothing, no difference, no change, H sub 0. And the alternative hypothesis is H sub A, well, because A is the first letter of alternative. In the free throw shooter example, our hypotheses are H sub 0. And the way this is written is important, please take note of it. Colon, not equal sign, not dash, right, colon. P equals 0.80, or 80% as a decimal. And the alternative hypothesis, H sub A colon P is less than 0.8. Right? the claim is the null, the thing we think might happen, or the thing we're checking for evidence for is less than 80. And then we define the variable, the parameter p, where p is the long run proportion of made free throws. You need all these parts to properly state a hypothesis. You need to say what the two claims are, the things you're comparing, and you must define the parameter, which means not just saying p is the proportion. What does it represent in context? Does anyone need a moment to write anything down from this slide? Please raise your hand. All right. In any significance test, the null hypothesis has the form h sub 0, colon parameter equals value. Right, the null hypothesis is equal. Get the equal sign. The alternative hypothesis has one of the forms. Parameter is less than value, parameter is greater than value, or parameter is not equal to the value. Right. It can be less than, it can be greater than, or just isn't the same as the value. To determine the correct form of the alternative hypothesis, we need to read the problem carefully. The alternative hypothesis is one-sided if it states that a parameter is larger than the null hypothesis value, or if it states that the parameter is smaller than the null hypothesis value. It is two-sided, in the last option, not equal to, if it states that the parameter is different from the null hypothesis value. It could be either larger or smaller. And that's what you'll see in like the word problems that set these up, is it will say, you know, so-and-so believes that they are exaggerating, or so-and-so believes that the percent is actually greater than that, or the proportion is less than, or the mean should be less than that, or that it's just different. I just think that this claim is not right. I think it's something else. All right. So you want to look for those cues as to whether or not your alternative will be less than, greater than, or just not equal to. See, we need a moment to write anything down from this screen. Things to remember. The hypothesis should express the hopes or suspicions we have before we see the data. You need to create your hypotheses before you run your sample. It is cheating to look at the data first and then frame hypotheses to fit what the data show. Hypotheses always refer to a population, not a sample. Be sure to state h sub 0 and h sub a in terms of population parameters. It is never correct to write a hypothesis about a sample statistic, such as p hat or x bar. Mainly, we don't have a sample to make those values from. We haven't ran it yet. We're making a hypothesis based on a claim. The claim is about a parameter. Okay. So suppose a basketball player claimed to be an 80% free throw shooter, as we considered earlier. To test this claim, we have him attempt 50 free throws. He makes 32. His sample proportion of made shots is 32 out of 50, or 0.64. We can conclude about the claim base. What can we conclude about the claim based on this sample data? We can use software to simulate 400 sets of 50 shots, assuming that the player is really an 80% shooter. And this is getting into an idea of how we'll find these p-values in the next couple sections, but it's just an idea here now. You can say how strong the evidence against the player's claim is by giving the probability that he would make as few as 32 out of 50 free throws if he really makes 80% in the long run. Right, and we see here in our graph, we see our sampling distribution of p hat, and we see that only 3 of those data points are as extreme as 0.64 value, right? In 400 sets of 50 shots, there were only 3 times when our shooter made as few as the observed p hat equaling 0.64. Based on the simulation, our estimate of this probability is 3 out of 400, or 0.0075. All right. So essentially, the probability of this result or something more extreme than this result happening just by chance, if our claim is true, is 0.0075, really low. The observed statistic is so unlikely if the actual parameter value is p equaling 0.80 that it gives convincing evidence that the player's claim is not true. Right? We only have 2 possible explanations for the fact that he made only 64% of his free throws. Number 1, the null hypothesis is correct. Player's claim is correct, p equals 0.8, and just by chance a very unlikely outcome occurred. The alternative hypothesis is correct. The population proportion is actually less than 0.8, so the sample result is not an unlikely outcome. All right, these are the 2 explanations. It's not 2 answers. It's just saying, if this is what happened, this is the only 2 ways we could explain it. Right? Being statisticians, though, seeing something that is incredibly unlikely to occur gives us evidence against the player's claim. Right? An outcome that would rarely happen if the null hypothesis were true is good evidence that the null hypothesis is not true. Essentially, it's like we just saw something happen that if this thing is true, shouldn't really happen. Right? That's not helping this person's claim. Right? Is there anything I can clarify so far? Any questions? So that brings us to p-values. The null hypothesis, h sub 0, states that the claim that we are seeking evidence against, the probability that measures the strength of the evidence against the null hypothesis is called a p-value. Notice it's not evidence for the null hypothesis, it's evidence against the null hypothesis. The probability computed assuming h0 is true that the statistic would take a value as extreme as or more extreme than the one actually observed is called the p-value of the test. We'll discuss how to calculate p-values in 9.2 and 9.3. Right now we're not calculating them. Small p-values are evidence against the null hypothesis because they say that the observed result is unlikely to occur when the null hypothesis is true. Large p-values fail to give convincing evidence against the null hypothesis because they say that the observed result is likely to occur by chance when the null hypothesis is true. Right, so small p-values, evidence against. Large p-values, not necessarily evidence against, but it's not enough to say that it's not true. See, we need a moment to write anything down from this screen. The final step in performing a significance test is to draw a conclusion about the competing claims you are testing. We make one of 2 decisions based on the strength of the evidence against the null hypothesis and in favor of the alternative hypothesis. We can either reject the null hypothesis or fail to reject the null hypothesis. Those are the 2 basic options. A fail to reject the null hypothesis decision in a significance test doesn't mean that h sub 0 or the null hypothesis is true. For that reason, you should never accept the null hypothesis or use language implying that you believe the null hypothesis is true. Think of the 2 claims as the judicial system, so to say, right? We have a system set up, supposedly, that people are assumed innocent until proven guilty. The null hypothesis is the assumption of innocence. The alternative is that they could be guilty. It's the prosecutor's job to provide enough evidence for us to reject the assumption of innocence, right, as like a jury, correct? If they do not give enough sufficient evidence to reject that assumption, then we fail, right, to reject that, which means maybe they are innocent, maybe they aren't, but the evidence isn't enough to support us saying that they're not. Right, so in that context, that's one like practical way to kind of think about this and why we have those terms. In a nutshell, our conclusion in a significance test comes down to p-value being small, then we reject the null hypothesis, and we have convincing evidence for the alternative. The p-value is large, then we fail to reject the null hypothesis. We do not have convincing evidence for the alternative. Okay. And deciding what is small and large is what we'll see next. Does anyone need a moment to write anything down? Please raise your hand. So there is no rule for how small a p-value we should require in order to reject the null hypothesis, but we can compare the p-value with a fixed value that we regard as decisive, called the significance level. We write it as alpha, the Greek letter alpha. It's like a fancy looking A. If the p-value is smaller than alpha, we say that the data are statistically significant at level alpha. In that case, we reject the null hypothesis and conclude that there is convincing evidence in favor of the alternative hypothesis. Right, so when the p-value is smaller than our alpha, it is statistically significant, and we reject the null hypothesis. Right, we can use a fixed level of significance to draw a conclusion in a significance test. And we get this kind of a logic. P-value is less than alpha, then we reject the null hypothesis. We have convincing evidence for the alternative. P-value is greater than or equal to alpha. We fail to reject the null hypothesis. We do not have convincing evidence for the alternative. Right, so this is kind of like a little roadmap from p-value to a conclusion. Okay, using our significance level. And you will typically be given a significance level or something to use as the significance level when trying to make these conclusions. If you're not, then the p-value will be evidently large or small. Would anyone like a moment to write anything down? Please raise your hand. So then we've made our conclusion. There's a possibility of two types of errors. Right? Well, we hope that we were correct, right? But sometimes we'll be wrong. There are two types of mistakes we can make, called type 1 and type 2 errors. If we reject the null hypothesis when the null hypothesis is true, we have committed a type 1 error. If we fail to reject the null hypothesis when the alternative is true, we have committed a type 2 error. Okay, and again, we try to avoid these types of errors by sampling well. Hopefully we have unbiased samples and all that fun stuff, and that helps us to avoid these types of errors, but sometimes they will happen. This little table here gives us a nice little way to check what type of error we have or if things have gone nicely. Right, along the top, we have the truth about the population, and then across the left here, we have the conclusion based on our sample. If our sample leads us to reject the null hypothesis, but the null hypothesis was true, that's type 1 error. If our conclusion based on the sample, we reject the null hypothesis and the null hypothesis is false because the alternative is true, we've done this correctly, right? We can also possibly fail to reject the null hypothesis based on our sample, and we shouldn't have, right? It is true, so we get a correct conclusion. And lastly, we fail to reject the null hypothesis, but we should have rejected it because the alternative is true. That's type 2 error. And it says a little table that you can use for reference based on your conclusion, the type of error that may have occurred. Right. Different errors have consequences. The probability of a type 1 error is the probability of rejecting the null hypothesis when it is really true. This is exactly the significance level of the test. Right? There is a way to calculate the probability of a type 2 error, but we're not there yet. A type 1 error is simply whatever alpha it was, right? Whatever you're comparing the p-value to for significance. Right? The significance level alpha of any fixed level test is the probability of a type 1 error. That is, alpha is the probability that the test will reject the null hypothesis when the null hypothesis is actually true. You always want to consider the consequences of a type 1 error before choosing a significance level. Right. So this is significance testing in a nutshell. We have hypotheses, we have p-values, we have significance levels, and we have errors. Right. We can reject our null hypothesis, we can fail to reject it, we may have evidence for or against the alternative. Right. These are the types of things we're going to be looking at. So we have some examples to look at here to maybe help this make a tiny bit more sense. So we'll look at those now. In our first example, we want to state an appropriate null and alternative hypothesis for this given context. And here we have hemoglobin is a protein in red blood cells that carries oxygen from the lungs to body tissues. People with less than 12 grams of hemoglobin per deciliter of blood, grams per DL, are anemic. A public health official in Jordan suspects that Jordanian children are at risk of anemia. He measures a random sample of 50 children. All right. The only value we have to use here is the 12 grams of hemoglobin. All right, because that's our value, the null hypothesis must be equal to 12 grams per deciliter. The alternative, which is the thing we're trying to find evidence for, is that is less than 12 grams per deciliter. So we get the following as our hypotheses. The null hypothesis is that mu, we're thinking 12 grams, the whole number, the average, right, is equal to 12 grams per deciliter. The alternative is that mu is less than 12 grams per deciliter. And then the last part of this is where we define the parameter, where mu is the true mean amount of hemoglobin per deciliter of blood in all Jordanian children. This is our population, Jordanian kids, right? Mu is a population parameter. Okay. Is there anything I can clarify about how this solution came to be? Here's another scenario. Simon reads a newspaper report claiming that 12% of all adults in the US are left-handed. He wonders if the proportion of lefties at his large community college is really 12%. Simon chooses an SRS of 100 students and records whether each student is right or left-handed. All right. So in this case, our parameter will be P, because we're dealing with proportions of left-handed students. Right. We have 12%. will be our null hypothesis, that the proportion is actually 12%. The alternative, right, considering that Simon doesn't care if it's more than or less than, because that wasn't stated, it's just different than, will be not equal to. All right, so we have a null hypothesis of p equaling 0.12, 12% is a decimal. The alternative is that p is just not equal to 0.12, and our defining of the parameter p, where p is the true proportion of lefties at Simon's large community college. All right, again, all of these things must be present to have an appropriate null and alternative hypothesis. If all you give is the variables and values here, that is incomplete. You need this second part of the phrase that says exactly what p represents in this context. What is that parameter representing? Any questions? Next example here, for the study of Jordanian children that we previously considered, the sample mean hemoglobin level was 11.3 grams per deciliter, and the sample standard deviation was 1.6 grams per deciliter. A significance test yields a p-value of 0.0016. Explain what it would mean for the null hypothesis to be true in this setting. This question is not asking for us to make a conclusion about what this p-value means based on the context and based on our hypotheses, right? We just want to say what the null hypothesis means. If it was true, what would that mean? Right? And that would just mean that Jordanian children would not be at risk of being anemic on average. Right? If our null hypothesis is true, that's what it means, because the mean hemoglobin level would be 12 or possibly more, but it's not less than, so we're good. No risk. Next question is interpret the p-value in context. This again is asking, what does the p-value mean? What is this a probability of based on this context? We're not being asked to use the p-value to make a conclusion about our hypotheses. So in this case, the p-value, right, is gotten by assuming the mean hemoglobin level of Jordanian children is really 12. There is a 0.0016 probability of getting a sample mean of 11.3 or smaller just by chance in a random sample of 50 children. That's what the p-value is. It's a probability of getting that result or something more extreme than that result merely by chance, assuming that the null hypothesis is true. Okay. Is there anything I can clarify about this? These questions, you have to read them carefully because they're asking different things. They're not asking for us to necessarily make a conclusion yet. So the last part of this question is, what conclusion would you make if alpha equals 0.05, or if alpha was 0.01? Justify your answers. Now we're using the p-value, comparing it to a significance level and making a conclusion. In both cases, right, the p-value is less than alpha, and we reject the null hypothesis. We have convincing evidence that the true mean amount of hemoglobin in Jordanian children is less than 12 grams per deciliter. And again, this is because we have a probability that if our assumption is true, if the null hypothesis is true, this result probably shouldn't have happened. Right? The probability of it happening just by chance is incredibly low. So the fact that it did happen in our sample gives us evidence against the null hypothesis and for the alternative. Okay. And this is where it becomes kind of useful to use like one of those like logic progressions that we saw earlier to make the conclusion. One more example with a couple parts to it here. Opening a restaurant. So you're thinking of opening a restaurant and are searching for a good location. From research you have done, you know that the mean income of those living near the restaurant must be over $85,000 annually to support the type of upscale restaurant you wish to open. You decide to take a simple random sample of 50 people living near one potential location. Based on the mean income of this sample, you will decide whether to open the restaurant there. So part A, we want to state an appropriate null and alternative hypothesis and be sure to define our parameter. So we get a null hypothesis that the mean is equal to 85,000. And the alternative is that the mean is greater than 85,000, where mu is the mean income of all residents near the restaurant. Right. So again, always default to the null hypothesis being equal to the value. And the alternative is the thing we're hoping for. We hope that the mean income is greater than 85,000 because then we found a good location. All right, based on the same context, what would be a type 1 and type 2 error, and what would be the consequences of each? Okay. So let's see. A type 1 error would be finding convincing evidence that the mean income of all residents near the restaurant exceeds 85,000 when it really does not. Because again, a type 1 means we reject the null hypothesis, meaning we have found evidence in our sample for the alternative. The alternative was that it was greater than 85,000. The consequence is that we opened a restaurant in a location where residents can't support it, okay, and our restaurant may not succeed. The type 2 error means we did not find convincing evidence that the mean income of all residents exceeds 85,000 when it really does. Right? We failed to reject the null hypothesis. The consequence is that you will not open your restaurant in a location where residents could have supported it and you lose potential income. You maybe choose the wrong location. So when considering a consequence of an error, type 1 or type 2, you want to consider what would be a real life, so to say, consequence. What would happen if this person were to open that restaurant and their data finding was incorrect? Okay, so that's when it asks for a consequence, it's really asking for what might happen if that was the actual error. Is there any other questions, comments, or clarification I can provide on these examples or anything else we've seen? So then we get to the end of the presentation. Right, hopefully we have an idea now of how we are supposed to state a null and alternative hypothesis. For a significance test about a population parameter, we have an idea of how to interpret a p-value in context. We have a method for determining whether the results of a study are statistically significant, and we are able to make an appropriate conclusion using a significance level. And we have an idea of how to interpret a type 1 and type 2 error in context and give a consequence of each. We've at least seen examples of these things, and we'll get more practice tomorrow. So that's the introduction to significance testing. Tomorrow we'll have a Desmos activity that we will do to get some practice on this. We'll have hopefully be able to gain a little more understanding of this, and then when we get into 9.2 and 9.3, we'll just be focusing more on the math side and then applying these same ideas to our results. If you have any other questions, comments, concerns, need support on anything from this lesson or previous lessons, please feel free to stick around on this call at the end and let me know, or you can just send me a message or an email later and ask for help. Other than that, that is the end of the lesson. I hope you guys have a wonderful rest of your day, and I will see you tomorrow.